Hello again, grade 12s. Welcome back to our next video lesson. So today we're going to be discussing the other types of reactions, but first I would like to just go over the corrections for the questions that I gave you for homework. So before we start, I just want to refer back to some of the notes that we previously did. So the first thing I just wanted to take note of is that we've already spoken about how esterification is an acidic catalyzed reaction between an alcohol and a carboxylic acid, which produces an ester and water. Okay, you must be able to identify the appropriate reaction conditions. So I just wanted to make note of just some additional points under esterification. So the reaction conditions which go above the arrow is the presence of the concentrated acid catalyst, and the second condition is that there will be gentle heating. Okay, it's heating, but the SAGS document specifically refers to gentle heating. So just make sure that that is the terminology that you're also going to use. Now, remember I distinguished that esterification is a type of elimination reaction and that combustion is the type of substitution reaction. However, one thing that I've noted on the SAGS document is that they have specifically noted right at the end of the very last point in the SAGS document. It explains that for combustion and esterification reactions, there is no distinction between the general and the specific type of reaction. So if you are asked for the type of reaction, you cannot say substitution if it is combustion, and you cannot say elimination if it is esterification. So if they ask you for the type of reaction and you know it's combustion or it is esterification, then you must say combustion, not substitution, or esterification and not elimination. Okay, they don't distinguish between the general and the specific type of reaction, which means that for those particular two reactions, if they say what type and it's combustion, you just say combustion, you don't say anything else. Or if it's esterification, you say esterification, you don't say elimination. Okay, so moving on, exercise 41. So it first asks you, write down a balanced equation for the reaction that occurs when a cigarette lighter is ignited in sufficient oxygen. So what's inside a cigarette lighter is butane. Now you need to write the molecular formula for butane. I hope that you realize that. So the molecular formula for butane, you can draw out butane if you want to, but if you can remember the general formula would be C4, which would make H2 times 4 is 8, plus 2 is 10. So technically butane would be C4, H10, plus oxygen, because it's reacting with oxygen. And remember, I already said that it's always going to form carbon dioxide and water. And because it's an exothermic reaction, you can, in this case, include the fact that energy is going to be released as well on the reactant side. Okay, so just to take note of that. So now if we're balancing it, we would first start, the best place to start would be with your carbon. So you would have 4 here to make 4 carbon. You have 10 hydrogens, and there's 2 here. So then I will put a 5 here to make 10. And then I notice, well, 4 times 2 is 8 oxygen, and 5 oxygen here, which means that you would have 13 oxygen. So if you know the trick here with this is that if that's the case, then you would put 13 in front of the O2 and you would double everything else. Then it will be balanced. So if you put 13 in front of the O2 and you double everything else, you would have 2 here because there was originally 1. The 4 would become 8 and the 5 would become 10. And then if you check, you'll see that now it is balanced. Okay, then it says, what makes the reaction of butane suitable for use as fuel in cigarette lighters? So the reason here that we are accepting is just the fact that, well, remember, it's releasing energy. So that's the main reason why it is suitable for cigarette lighters, is because large quantities of energy is released. Well, it would be are released. Are released. Okay, is this reaction exo or endothermic? Give a reason for your answer. Okay, of course it's going to be exothermic. And the reason for the answer is that energy is released. Okay, then it says hexane is found in some fuels. The combustion of hexane is complete. Which products forms during the combustion? So it will be CO2, H2O, and energy. Give a balanced equation for this reaction. So again, hexane would have the formula C6H14 plus O2, which would give you CO2 plus H2O. Now, if you use the same method that I've used above, then you can get the following balanced equation. So you'll see that there's 6 carbon, 7 times 2 to make 14, but then you would notice that 6 times 2 is 12 oxygen, and 7 oxygen here would make a total of 19. So if you put 19 here and double everything, then you will have a balanced equation. So 6 becomes 12 and 7 becomes 14, plus energy. Okay, then it says, why is there harmful carbon monoxide in the exhaust fumes of cars? So the reason why there is harmful carbon monoxide in the exhaust fumes of cars is because of incomplete combustion. So when there is incomplete combustion, then instead of forming carbon dioxide, it forms carbon monoxide, which is far more toxic than carbon dioxide. So the reason why this occurs is because of the incomplete combustion that takes place in a car engine. Okay, and the reason why it's incomplete combustion is because there isn't sufficient oxygen present. So there is not enough oxygen present in order for complete combustion to take place. Okay, so that's just something to take note of, is that combustion reactions can either take place completely or incompletely. If it takes place completely, then there's sufficient oxygen to form carbon dioxide in water. And if it takes place incompletely, then it would form carbon monoxide. Okay, so now question 4 says, write down a balanced chemical equation for the following. Octane burns in sufficient oxygen, so that will be 2 C8H18 plus 25 O2, which will become 16 CO2 plus 18 H2O plus energy. Hexane burns in sufficient energy. Okay, it's going to be the exact same as insufficient oxygen, sorry, is going to be the exact same as the one above. And then propane burns in sufficient oxygen. propane has the formula C3H8 plus 5 oxygen molecules will form 3 carbon dioxide molecules plus 4 water molecules plus the energy. Okay, then it says give a balanced molecular formula for the following reactions. Methanol, okay, they spelled methanol wrong, but methanol burns in sufficient oxygen. So methanol, you can either write the full condensed formula, the molecular formula, but I'm going to write the condensed formula like that with the OH. Okay, you can also write it as CH4O is also fine, but normally we don't like it like that because it's nicer to see it like this, because you can see, oh, immediately that's an alcohol. Okay, then we would add that to oxygen to form carbon dioxide plus water plus energy. Okay, and then if you balance it, it would be 2 CH3OH plus 3 O2 would form 2 CO2 plus 4 H2O. Okay, then methyl hexane burns insufficient oxygen. So methyl hexane, hex is going to be 6 carbon, sorry, plus a methyl group would make a 7th oxygen. So it would be C7, and then using your general formula, you would have H16 plus O2, which would form CO2 plus H2O plus energy, and then you just balance it. So you would have 7 CO2, 8 H2O, and then 7 times 2 is 14, plus 8 would give you 22, so you just put in 11 and you're done. Okay, then it says give the IUPAC name for the following. Okay, so we can see that 6.1 is just a carboxylic acid with 3 carbons, so it's going to be propanoic acid. Okay, then moving to the next one, we can see that the next one is an ester. So the side that's next to the single bond oxygen is 1 carbon, so that will make it methyl. And then the carboxylic acid part has 2 carbons, so that would be ethanoate. Okay, the next one is also an ester, so that one we're going to, it's also a methyl for the alcohol part, and then there's 4 carbons on the carboxylic part, so it's butanoate. Okay, then the next one is just an ester. I mean, not an ester, it's a carboxylic acid. I can see the functional group is on the terminating carbon with 5. So that's going to be pentanoic acid. Okay, then it says give the structural formula for the following 2,2 dimethyl propanoic acid. So we would start by first doing our 3 carbons, 1, 2, 3. Then it says it's on the second carbon is the 2 methyl group, so it'll be 1, 2. Remember, even if they said dimethyl without giving the numbers, you must still know that obviously it's on the second carbon. Okay, it can't be on any other carbon. So there isn't any indication that you would lose marks for a prop molecule with side chains, because you can either say 2,2 or you can just say dimethyl propanoic acid. It's fine. Then 2,3 dibromopentanoic acid. So we start with our 5 carbons first. 1, 2, 3, 4, 5. And then it says it's on the second and the third one. So because it's pentanoic acid, I'd first put my functional group in on the end, and then start numbering from the functional group. So if it's 2, then it would be on this one, and then 3 would also be on the next one, and then you would just fill in the rest with hydrogens. Okay, then number 8 says draw the structural formula for the following reactions. Ethanoic acid reacts with methanol in the presence of heat and concentrated H2SO4. So you would start by putting your ethanoic acid, which would be 2 carbons, you can also start with the alcohols, fine as well, plus the methanol, which will be COH, and that would form with the presence of an acid, H2SO4, and heat. You would have, I'm not going to have enough space for this, let me move up. So ethanoic acid plus methanol would form methyl ethanoate. So you would have your ethanoate part and then your methyl part. Plus the water. Okay, then the next one, it says in which an alcohol reacts with a carboxylic acid and produces ethyl butanoate. So if it's ethyl, then the alcohol is ethanol. So it will be C, your H's, OH, plus then it says butanoate, so it would be butanoic acid. And that would react with H2SO4 and heat to form the actual ester that they gave you, which was ethyl butanoate. So hopefully I'll have enough space. So we'll start with the alcohol, then the carboxylic acid has 4, 1, 2, 3, 4. Make sure you keep the double bond in the right place and you have the right number of carbons on each part. Sorry, I put an extra hydrogen here. H, and then plus the water. Okay, don't forget the water as well. So then question number 9, it asks you to complete the table. So butanol plus propanoic acid would make butyl propanoate. Then methyl ethanoate will be made from methanol and ethanoic acid. Then ethyl methanoate will be made from ethanol and methanoic acid. Propyl methanoate will be made from propanol, and more specifically, be careful because it would be a primary alcohol, so that would be propan 1-ol. You can't just say propanol and methanoic acid. Okay, it has to be with a what we would call a primary alcohol. So that would mean that the hydroxyl group is found on a terminating carbon. So could never be propan 2-ol, but you must still say propan 1-ol to show that you know that, and that is how we name it. We always name alcohols by indicating the number with which the hydroxyl group is found. Then propan 1-ol plus pentanoic acid would form propyl pentanoate. Pentan 1-ol plus methanoic acid will form pentyl methanoate. Then propyl butanoate will be formed from propan 1-ol and butanoic acid. And heptan 1-ol would be heptyl butanoic acid would form butanoate. Okay, then it says butyl butanoate is an ester with a pineapple scent. It can be prepared from an alcohol and carboxylic acid. Write the structure roll formula for the ester. So it's butyl, so the alcohol part will have 4 carbons. 1, 2, 3, 4. And then put in all your hydrogens. And then butanoate would then form 4 carbons on the carboxylic acid end. So you have 1, 2, 3, 4. Okay, be careful, don't add extra carbons. Okay, make sure you count the carbon that's attached to that double bond. Okay, then it says give the structural formulae and IUPAC names of the alcohol and carboxylic acid used to prepare butyl butanoate. So it will be butyl because is butan 1-ol. So it will be 1, 2, 3, 4 OH. So you write the IUPAC name is butan 1-ol, and then the carboxylic acid, because it's butanoate, will just be butanoic acid, which would have the 4 carbons, double bond O, single bond OH. Okay, so make sure that you've put in all the correct hydrogens. Make sure that you've done everything correctly. Okay, so always double check that you've put in the right number and then you move on. Okay, which catalyst is used in this reaction? So it is, you cannot just say sulfuric acid, it is concentrated sulfuric acid, okay, because that's very important. It can't be a dilute sulfuric acid, otherwise it doesn't work in a similar way. Okay, so then question 11. So it says large volumes of alcohol are produced globally every year. Some of the production comes from fermentation processes of that alcohol is used for alcoholic drinks. Most alcohol ever is produced from other sources like natural gases and petroleum. Ethanol can be used in a number of industries. One potential use is in the production of scents by making esters. So alcohols are actually used in a lot of perfumes. So that's what often gives it that scent, because it reacts with some sort of carboxylic acid. So one of your chemistry practicals is to prepare an ester. It is expected for you to choose an appropriate chemical that can be used with ethanol. The chemicals you can choose from are concentrated sulfuric acid and propanoic acid. For the following 2 questions, mark the letters that correspond to the answers. The function of the sulfuric acid is to oxidize ethanol, reduce ethanol, dehydrate ethanol, or to catalyze the reaction. Okay, so the main point of the acid is to act as a catalyst, which means that the answer is D. Then 11.2 says the process includes the ethanol losing an H, ethanol gaining an H, the formation of water, or propanoic acid losing CH3. Okay, so the process of this taking place, remember the ethanol, the alcohol doesn't lose, it's not losing an H or gaining an H, okay, but rather the process would include the formation of water. Okay, so that is the answer that we are looking at specifically for that one. Okay, so just take note of that. Then it says, what will you observe at the end of the experiment? So what you would observe is the distinctive odor of whatever we're trying to produce. Distinctive odor. Okay, so make sure that you've understood before moving on, but that would mark the end of that exercise. Okay, so then you can write the date and the heading. So we're going to look at the other types of reactions. So I'm still going to write organic reactions. Okay, and the heading is going to be the date is the 13th. Okay, so like we previously established, right? There are three other types of reactions that you have to learn. So it's the addition, the substitution, the elimination, and the substitution. Okay, so I would like to start with substitution reactions because I just think that they are the easiest and they don't really require too much rules. So when we look at substitution reactions, so it's important to remember that this reaction is the general reaction, the general type. So if you are asked, what is the general type of the reaction? Then you will say substitution. Okay, so just take note of that. That's quite important. So you must be able to identify and also to give the products of a specific type of substitution reaction. So there are two types of substitution reaction. The first type is called halogenation, and it kind of gives into its own name where it is an alkane plus a halogen. Not plus a halogen, it's a alkane, I wanted to say, which forms a haloalkane. Okay, so yeah, we are still going to add a halogen, but I just wanted to specifically just show you from an alkane to a haloalkane. So for example, it would be like taking methane and adding chlorine would form the haloalkane plus whatever remains, so it would be like an HCl. Okay, so the condition for this reaction, which you have to learn off by heart, is that, let me write condition, is it must take place in the presence of ultraviolet light, let me just write it properly, ultraviolet or UV light and heat, or heat, so either one, or heat. Okay, so if you have a look at this table again, you'll see that we already said that the substitution, I'm highlighting it using the pink color. So substitution reaction, the one that we're specifically looking at is the halogenation, which is from an alkane to a haloalkane. So the substitution takes place with a halogen, and you would have the haloalkane byproduct, and it must take place in the presence of sunlight or UV rays. Okay, so the next one, the second type, is called hydrolysis. Hydrolysis. So hydrolysis is from a haloalkane to an alcohol. Okay, so for example, you would take let's take the CH3Cl that we've already done. If I add that to dilute NaOH, it would form an alcohol, CH3OH, right? The OH would come from the base, and then I would have NaCl as a product. Okay, so the reaction condition for this particular reaction is that it must be, let me write conditions, is heat under reflux, in a dilute alkali solution. So if you have a look here, I don't think that hydrolysis is actually one of the things that they include here. So we can just say, well, you can add your own one, that from a haloalkane to an alcohol, it's going to be a substitution. So I guess it should actually be a dotted line. So let me make it a dotted line then. Okay, and then I'm also going to highlight it. So this is a substitution reaction where if you use, so you would need heat under reflux, and you would also need an aqueous alkali solution, so like NaOH, aqueous. Okay, so what this entails, right, is that the haloalkanes essentially react with the OH part of that hydroxide, of the alkali solution. So the reason why we use an alkali solution is because of that OH that we need in order for the alcohol to form. So the product for this situation, we'll have a haloalkane plus a hydroxide, which would form an alcohol plus a halide salt. Okay, so when the haloalkane is, is solid, it's dissolved normally in some sort of ethanol, and then when it comes into contact with a aqueous dilute alkali solution, such as sodium hydroxide here or potassium hydroxide solution, we usually require an excess amount of water, and then the mixture is then heated under reflux. Okay, so you must know what this heat under reflux refers to as well. So heat under reflux, what this basically means is, it means that we use like a particular type of apparatus to do this. So it's when the reaction is heated for a specific time, and while the vapor is continuously cooled back into a liquid using a condenser. So the condensed vapor then returns to the flask as a condensate. So heat under reflux, you can basically say, is when the reaction is heated while the vapor is cooled back into a liquid. Using a condenser with an ER. Okay, so it's almost like we would have this condenser, and inside this, so this condenser would have like some sort of water outlet. Okay, then there would be the solution would be at the base that we're obviously trying to heat. So there would be some sort of heating source at the bottom. So as we are continuously trying to heat this up, there is this additional tube that is placed inside of the flask, which condenses it. So essentially you would have this flask which would be open here, and it would be clamped. Let me draw this a little bit higher. It would essentially be clamped in place here. So what happens is that when the condensing vapors go within this container, but then there's this water outlet that exists that is going to essentially allow water to go in. So normally there's an outlet here where you put cold water, and then the cold water sort of surrounds the container on the sides and then is released through the outlet. And then what happens is that as this vapor is sort of getting hotter, it kind of just then condenses back into this liquid state, because obviously we don't want to lose any product. So that's what the main purpose of this heating under reflux is actually referring to. Okay, and the SAGS does make mention of the fact that this is something that you must know. You must know what it is and what the purpose of it is for. Okay, so that's the substitution reactions. Now, when we look at the addition reactions, well, first, I want to make note that it is only saturated compounds that can go through substitution. So we've done the halogenation, we've done hydrolysis. So important to note is that it is only saturated compounds that go through substitution. And remember, we did the other type of the combustion, but we don't refer to that necessarily as a substitution. You just refer to that as combustion. Okay, then the next type of reaction is addition reactions. So with addition reactions, now addition reactions occur with unsaturated compounds. So this is a nice way to kind of help you to start remembering, is that the substitution occurs with saturated and addition will occur with unsaturated compounds such as the alkenes. So the double bond is broken and becomes a single bond, and then addition is usually faster than substitution because alkenes are more reactive than alkanes. Okay, so in general what happens is that some sort of alkane with that double bond is going to react with a substance XY, and that substance will then form a single bond with the X and the Y being added to the remaining bonds. Okay, I won't put the H's in because it could still continue with more carbons on either side. Okay, so again, addition reactions is the general type of reaction. So this is what you would say if they asked you for the general type. Okay, so addition is a little bit more complex in the sense that there are 4 types of addition reactions that we look at. So the first type of addition reaction is called hydrohalogenation. Hydrohalogenation. Okay, hydrohalogenation. So this is what happens if you add a hydrogen halide. Adding a hydrogen halide. That's what's called hydrohalogenation. So examples of hydrogen halides is like HBr or HCl or HI. Okay, so it forms the corresponding haloalkane. Okay, so if we look at the conditions, the conditions of this reaction is that there must be no water present. Okay, the reason why there's no water present is because if there was, then hydration would take place, which is a different type of addition reaction. So if there was water, there'd be a different reaction, and then alcohols would form during this reaction. So if the alkene is solid, it must be dissolved in some sort of non-polar solvent like a hexane or benzene. So you cannot, this specifically, you cannot have water present in this. Okay, so when it comes to now the products that is going to be formed, Okay, we look specifically now at some rules. So we would start by saying, okay, if we look at the rules, so let me take an example like, let me just find an example. Let's say we took propene. So if I decided propene like C, we take prop 1 in, and we added some sort of H, and then we'll say X because remember it's a general reaction. So that is obviously going to then form whatever respective halo alkane is going to form. So I just want to move everything a bit closer just so I have a little bit more space. So if we see the product, we'll see, okay, well, there's already 3 carbons, so the 3 carbons would still stay in place. Now, what's very important here is to take note of what bonds were present and what bonds were not present. So let's say if I decided to just write the bonds that I had. Okay, I have 1, 2, 3, 1, 1, 2. So that's what I write here, 1, 2, 3, 1, 1, 2. Now, there's a special rule that we use here. Okay, so the rule that we use is called Markovnikov's rule. And what Markovnikov says is that the hydrogen atom will bond to the carbon atom which has the greatest number of hydrogen atoms bonded to it. So the H atom bonds with the carbon atom with the most number of hydrogen atoms. So if I had to look at this above, right, I can see that the one between, obviously this carbon can't take any more bonds. Okay, this one already has the hydrogen, so I'm going to put those in. I'm trying to figure out if there's a hydrogen here. Okay, this says that, well, remember the hydrogen is going to have to go somewhere and the X is going to have to go somewhere. Now we need to think, is the X going to be here or is the X going to be here? We don't know. But Markovnikov's rule says that the hydrogen bonds to the carbon with the most hydrogen. Now this carbon here has 1 and this carbon here has 2. So according to Markovnikov's rule, the hydrogen will bond to the carbon, and what will be left then is the X. So the X would bond specifically to that. So this is what we call the major product. And then if the other form had to be formed, we would call that the minor product, where the H, so there could be some that forms, but it's not a lot at all. So this is called a minor product because it is still possible for it to form. However, this is what we know forms according to Markovnikov's rule. So if you go look at your sheet, you'll see, okay, well, your addition reactions now we'll do in yellow. So the first addition is the hydrohalogenation, which is an alkene to a haloalkane, And you can even make a little note here for yourself to say no H2O must be present. Okay, that is one of the important conditions. Okay, then if we look at the next type, so there's going to be quite a lot and we're going to go through all the types. So the next type is, we did hydrohalogenation, now we'll do hydrogenation. So hydrogenation is now if we are adding H2 to the alkene. So we're not adding, so notice how you learn it. Hydrohalogenation is adding a hydrogen halide, like HBr. Then hydrogenation is adding H2 to the alkene. Okay, so the reaction conditions is that the alkene must be dissolved in some type of organic solvent. Must be dissolved. Sorry, the pen's still not working with me. The alkene must be dissolved in an organic solvent. So an example of this would be, an organic solvent with a platinum, palladium, or nickel catalyst in an H2 atmosphere. Okay, so we want the alkene to be dissolved in some sort of organic solvent with a platinum, palladium, or nickel catalyst in an H2 atmosphere. Okay, so I know that might seem a little bit complicated, but that is essentially what we're trying to learn. You just remember that off by heart. Okay, so an example would be like if we just took any alkene. So let's take prop-1-ene again. And I said, okay, well, if I added this to an H2 molecule, then again, I'm going to break up the double bond. Okay, so I already had 2 hydrogens present on the carbon to the left, 1 in the middle, and 3 on the right. And then this one is much easier. We don't have to worry about Markovnikov's rule because both H's will just bond to the remaining carbons, and then you will have an alkane. So essentially you have H2 from an alkene, and it forms an alkane. So if you go to this chart again, we'll see that hydrogenation plus H2 will form an alkane, and the specific conditions is having the PT, but you can also add that it would be PD as well as Ni catalyst as well. Okay, then moving to the next type of addition reaction, we have so we've done hydrohalogenation, we've done hydrogenation, now we look at halogenation. So halogenation is if we add a halogen. Okay, so just be careful because it's not a substitution reaction. So it has a it's similar in name, but this causes something different. Okay, so it's when we add X2, right, where X is either going to be chlorine or bromine. Okay, so what happens is, and remember the reaction conditions are also going to be different here. So the conditions if we have a look at our flow chart, halogenation requires, well, in this case, yeah, the sunlight, UV as well. Okay, so you can see that the conditions is still similar in the sense that you still need the sunlight. Oops. Sunlight or UV light. Okay, so you must know that rapid discoloration of bromine water by an alkene at room temperature is used to distinguish an alkene from an alkane. Okay, so to distinguish between an alkene and an alkane, because remember, if you the first halogenation takes place from an alkane to a haloalkane. Now this one is from an alkene to a haloalkane. So the way that we distinguish in a lab the difference between an alkene and an alkane is through the rapid discoloration So when we add it to bromine water, it's going to discolor. Discoloration of bromine water by an alkene at room temperature. Okay, this is referred to as the test for unsaturation. So if you look inside that science clinic note, you'll see that it's on that first note. Okay, so since alkenes are more reactive than alkanes, addition reactions occur faster than substitution reactions. So it's quite important to know that alkenes are more reactive than alkanes, and so the addition takes place faster than substitution. Okay, so let's look at an example of the halogenation. So an example would be, let's add the halogen to, we'll do the same, we'll do prop 1ene. And again, you don't have to worry about the conditions, well, not conditions, the Markovnikov rule here, because again, the X's will just form the way that they did with the hydrogenation. So you would already have your H's present, and then the X's would just go to their respective carbons. Okay, then the last addition reaction that we look at is hydration. So if we go all the way to the top, we'll see, so hydrohalogenation is a hydrogen halide. Then hydrogenation is adding H2, hydrogen. Halogenation is adding a halogen. Okay, and then hydration is adding water. Okay, so think of like when you hydrate, you are adding water. Okay, so to an alkene. Okay, so the reaction conditions for this one is steam and a suitable catalyst. For the suitable catalyst that we could use would be H3PO4. Okay, phosphoric acid. So if we looked at an example now, let's take water, plus again we'll take the prop 1 in that we've been looking at. Two, three. So again, I'm just going to write out my propene with the bonds that were there and the bonds that are missing. So now the product that's going to form is an alcohol. Okay, because if you think about water, right, it's going to form an H and an OH ions. So now we have to think to ourselves, now remember, there's two spots, right? There's this carbon and there's that carbon. Now we need to figure out where does the H go and where does the OH go for the major product. So now again, we have to remember Markovnikov's rule that said that the hydrogen bond bonds to the carbon with the greatest number of hydrogens. So because this carbon has two hydrogens already, it will bond to that, and then the OH will bond to the second carbon. Okay, so those are the types of addition reactions. Okay, then the next type of general reaction that we look at is called the elimination reactions. So these are the next general type of reactions. So with elimination reactions, there are three types. So the first, and they kind of work in opposite to the addition. So the first is dehydrohalogenation. So if we look at our chart, we see that, okay, the last one that we spoke about was the hydration, adding water. Okay, you add a suitable catalyst like H2SO4, or you could add H3PO4, it's still the same. So now we look at the elimination. Now the elimination is going to work opposite. So with hydrohalogenation, we would have dehydrohalogenation, which is removing the hydrogen halide. Okay, and then there's your condition: a strong concentrated base dissolved in ethanol. Okay, so the dehydrohalogenation is eliminating HX from any haloalkane to form that alkene again. Okay, so the conditions is that you must have hot concentrated NaOH or KOH in an ethanol solvent. So again, in the absence of water. So the amount of water produced in the second reaction is insufficient to cause hydrolysis. So we must make sure that there is still going to be that absence of water. Okay, so an example of dehydrohalogenation would be like taking your, let's take a butane with, we'll put the X on the second one. Okay, so what happens is that when this takes place in the presence of hot concentrated NaOH in ethanol solvents, so in the absence of water, it's going to form the products. So now the product that is going to be formed is going to be the HX, right? So it's going to remove the X, but now once it removes the X, it's also going to have to remove a hydrogen. So we have to figure out which product is going to be formed. Now we use a second rule. So we use Markovnikov rule for the addition. Now we use a second rule for the elimination, and this is called Zaitseev's rule. Zaitseev's rule. So Zaitseev's rule says that the H atom is removed from the carbon with the least hydrogen atoms. So when we look at this now, okay, we already know that we can draw the molecule again. So with pencil, you can copy and paste this over. So we know, first of all, that this X is going to be taken away. Now we ask ourselves, okay, is this hydrogen going to go with it, or is this hydrogen going to go with it? Okay, or this one, or this one, or this one. We need to figure out which one it is. So Zaitseev's rule says that the hydrogen atom which is removed is from the carbon with the least amount of hydrogens. So if I look at this now, I can see, okay, well, so I can't remove this hydrogen because I've already removed one thing from it. So I need to look at the two carbons next to the carbon where I've removed the X. Now this carbon here has 2. hydrogens. And this carbon here has 3 hydrogens. So according to Zaitsev's rule, the hydrogen that is removed is the one attached to the carbon with the least hydrogen. So the 2 will then become 1. So that hydrogen will be removed as well. And then the double bond would then form between the 2 that I removed the X and the H from. So the X was here, the H was here. So the double bond then forms between these 2. Okay, instead of, and the reason why I removed this hydrogen and not a hydrogen from here is because of Zaitsev's rule. So this is again called the major product, and then the minor product would be if it formed between the end carbon. Okay, so if we had something like, so this is the elimination reaction, but just on its own. But if we decided that we would add a base to it, it would still do the same thing. So if I said, let's take the same reaction. So if I take the same thing and I say, okay, well, what if I took this now and I decided to add KOH to it? So again, now what is going to be formed is that I'm going to have an ionic salt, I'm going to have water, and the remaining product I would still follow the exact same rule. So I would still use Zaitsev's rule, and I would still figure out, okay, well then the hydrogen that is removed is the one that comes from the carbon atom with the smaller amount, with the least amount of hydrogen. So then that would be the second product. So there's going to be 3 products if I add the base to it. It's just going to be this ionic salt, the water, and the remaining alkene product. Okay, and then the next type of elimination reaction is called dehydration. So dehydration has the meaning in its name. So if you are dehydrated, then you are losing water. So dehydration is going to be the removal of water. Dehydration. Sorry, it's still glitching out. Is the removing of the water. Okay, so if you look at the flowchart again, you'll see that dehydration acts in the opposite direction to hydration, where now we're going to have an alcohol which is going to form a alkene through removing H2O and having concentrated H2SO4. Okay, so it's the removal of H2O from an alcohol. Okay, so the condition for this reaction is that you must have an acid catalyzed, it's an acid catalyzed dehydration, catalyzed dehydration. So you heat alcohol in an excess of concentrated H2SO4 or H3PO4. So you heat the alcohol in concentrated H2SO4 or H3PO4. Okay, so an example of this type of reaction would occur, let's take butanol. We'll take butan 2-ol. And we would eliminate water. So if we have water, then the byproduct, we will rewrite this and we would tell ourselves, okay, well, remember what's being removed is firstly the H and the O. So now we ask ourselves, okay, well, which hydrogen is then going to be removed? Well, according to Zaitsev, it's the one with the least number of hydrogens bonded to the carbon. So if that's this carbon here, then the double bond would form between those two carbons, and I would remove that additional hydrogen there. Okay, so that is essentially how dehydration works. Okay, then there's one more type of elimination reaction that we'll do, which is called the cracking of hydrocarbons. So cracking of hydrocarbons. So that's kind of the last elimination reaction. So if we look at the two that we had here, we looked at dehydration, which is between concentrated H2SO4 by removing water, and we looked at dehydrohalogenation. So the last one is the thermal cracking. That's the one here on the left, where an alkane goes through some sort of thermal cracking to form an alkane and an alkene. So we break up these very large alkane molecules to form a mixture of smaller and more useful alkane and alkene molecules. Okay, so we are breaking large alkane molecules to form smaller alkenes and alkanes. So there are, the conditions is based on the type of cracking that we are looking at. So there are technically two conditions for two types of cracking. The first one is called thermal cracking, which requires high pressure and temperature with no catalyst, and we would have catalytic cracking, which I'm sure you can assume will be the opposite, which will be low pressure and temperature with a catalyst. Okay, so they will accept if in elimination the products that you are given. So just make sure that you do know how the major and minor products do still work, though, in case it is asked of you. So I'll just show you an example and then we'll be done. So we'll have, let's say, hexane, a very large organic molecule, and through some sort of cracking process, okay, in order to save time, I'm not gonna, let me draw the hydrogens quickly. So what will happen is that it will crack into some sort of smaller alkane and a smaller alkene. Okay, we're not too concerned with the products that are formed, and we're more concerned with the conditions. Okay, and those are basically all the types of reactions that you can be asked for. So we have substitution, addition, and elimination, which are all the general reactions, and then you must know what each reaction is, what the conditions are, when they take place, what product will form, and that's it. So for your homework and for practice, I'm going to give you exercise 42, question number 1 until question number 5 to do. Okay, so make sure that you go over that and that you practice. And it is a lot of work, but over time, if you segment the learning and you start learning them now slowly with the mind map that you have, then it will be a bit easier to do as the time goes on. Okay, I hope it makes sense, and then I will see you on the next one.